we are continuing with electricity circuits, and we're going to go over some more review for Ohm's law and use Ohm's law to be applied to a certain area of a circuit. We're relating the voltage in that area of the circuit to how much current is flowing through that portion of the circuit, as well as the resistance of that portion of the circuit. And it kind of stems off of our last, I did talk about Ohm's law a little bit with you last time, right?
Yeah, you did.
All right. So let me get my pen ready to go. All right, so Ohm's law. Do you remember Ohm's law?
Yes, I do.
So what is Ohm's law? All right, don't worry about your notes. So I'm going to just, last time I more or less told you what Ohm's law was, and I explained it, but this time I'm going to show you.
Okay.
All right? So give me a moment. All right, can you see the blue screen?
Yes, I can.
Okay. So I mentioned having a virtual app in our last session that I can use to create circuitry, and virtually. But we were running out of time. I didn't have time to use it last time. So I'm gonna show you what I wanted to show you last time. I'm gonna show you that today.
Okay.
All right. And I think it'll give you a better sense of what Ohm's law really is. And so Ohm, I think his name is Gregory Ohm. I think he was late 1700s, early 1800s. Was experimenting with circuits and trying to figure out if there are any patterns in any of the quantities and how the quantities related to each other in terms of voltage, current, and resistance. And he certainly did uncover a pattern, okay? And so I'm going to step you through in this virtual environment here what he was doing and how he actually discovered what became known as his law, Ohm's law, all right? So this thing that I just dragged in is called a resistor.
Gotcha.
And that's actually what they look like. Resistors are generally kind of small. I can show you pictures of real resistors. So you see those?
Yeah.
That's what they really look like. They're normally pretty tiny.
I'm familiar with that.
All right. And so in the virtual environment, it's similar. It looks similar. And so the purpose of a resistor, well, I won't say the purpose yet. Resistors inherently have an electrical resistance, meaning they resist the flow of electricity, right?
Yeah.
So they're not excellent conductors, because an excellent conductor has low electrical resistance and allows electricity to flow through it quite easily. While things that are called insulators typically have a very, not necessarily always very high, but a fairly high to perhaps very high electrical resistance. Those are called insulators. And so the resistors that I just showed you in those pictures, would those be conductors or would those be more on the insulating side?
Supposed to be more on the insulator side.
Exactly, yep, because they don't let electricity flow through them easily. It doesn't mean they stop the electricity from flowing through them. It just means it can be relatively difficult to make electricity flow through them. That's why they call them resistors, right?
Yeah.
Okay. So what I'm going to do is set up a circuit with you, and it's known as a series circuit. So first, actually, I'll go back to the drawing and show you that series circuit looks like something like this. You have a resistor right here. These would be cables, which are conductors, right?
Yeah.
Probably copper. In our real world, they're all made of copper on the inside. And then let's just say we had another resistor here, and then we put a battery like this. So this is battery, right? And the battery is what has the voltage, right?
Yeah.
Which means that it has negative charge stored on it, right?
Yeah.
And when you connect that battery to the circuit, all that negative charge that's inside the battery just comes flowing out, and it goes through your circuit. And that's what we normally refer to as electricity, right?
Yes.
Okay. So this is a series circuit, and the reason they call it series, because generally speaking, to be in series means to come one after the next. So whenever you have a sequence of things that comes one after the next, you call that a series. That's why we call it a television series. Because it comes one after the next, right? And so these are considered series circuit because if you were electricity, that this resistor, and then you would have no choice but to eventually be forced through the next resistor, and you would just keep on going, right? One after the next. That's why they call it a series. Does that make sense?
Yeah.
All right. So let's go back to the simulation now. And I'll build that. And in fact, I'm going to actually do it a little differently now that I think about it. I'm going to delete this resistor. So I'll eventually build the other one, but let's just start off with the simplest possibility, which is just one battery and one resistor. All right?
Okay.
And what you see right now is actually called an open circuit. And an open circuit means there's a gap, and therefore the circuit's not running.
Yeah. I'm familiar with that.
Okay, and then when you close the circuit, it's like this, right?
Yeah.
Yep. Okay. And so, do you know what this device here is called?
Multimeter?
Yep. Yeah. So, if you went to Home Depot to buy it, they'll probably have it labeled as a multimeter because it can measure multiple things. It can measure voltage, resistance, and current, depending on which setting it's on. Some people also just refer to it as a voltmeter, but generally they're referred to multimeters because they can do multiple things. So this voltmeter can be used to measure the voltage of the battery, and you would take these, they're called leads, and you would touch one to each end, and it would tell you what the voltage of the battery is, so you can see it saying 9 volts, right?
Yeah.
Okay, let's change it to be just a little bit nicer of a number rather than 9. We're going to call it 10 volts. 10's a little nicer to work with than the number 9 when it comes down to the math portion of it. So we now have a 10-volt battery, and let's say we don't know how much resistance that is, right? Let's just say it's unknown. I could technically click and find out, but let's just say we have no idea how much resistance it is. In fact, I would like it to be, I think it's a nice number. Yeah, it is. All right. So now what I'm trying to do is show you what ohm would have done. You would take a what's called an ammeter, which doesn't seem like it's coming into the screen right now. Oh, that's too bad. Oh, wait a minute. Why? Huh. It won't let me use the ammeter. I wonder why. All right, well, that's a big part of what I needed to show you, and it's not working. Shoot. Oh, that's right, I have to drag it in. Oh, it's because the join me thing is right over it. Let's see if I can I move the join me thing? Let's see.
What do you mean?
Oh yeah, I can move it to the other side. Okay, here we go. There we go. It was a join me thing that was in my way. The little symbol for the join me where it says you and all right. Anyways, let's see. There it is. Okay. All right. So when you want to measure current, you use this thing called. Do you remember what unit current is measured in? Like voltage is measured in volts. Current would be measured in. Good guess. That's actually charge. So the physical quantity of electric charge is called coulombs, but the flow of electricity is referred to as amps. Yep. And so this is actually called an amp meter. Okay. And what you would do is you would put it into your circuit so that the electricity is forced through this sensor. Okay. And notice it currently says 1 amp on there.
Yeah.
So I can turn it a little bit. Give me a second.
I can read it.
Okay. So it says 1 amp is flowing in this circuit. Let's go back over like this and measure our battery is 10 volts. Okay. So what Ohm would have done would be to make a graph now. And I'm going to make a graph and show you on Excel voltage versus current. Okay, so you see that when the voltage is 10 volts, the current is 1 amp, right?
Yeah.
All right, so let's go over to our here, and now I would just type in current and measured in amps, and I'm going to make a data set, and then I'm going to eventually graph it. Current versus voltage, or really voltage versus current. So the first data point would actually be, if there was 0 voltage, that means your battery is dead. How much current would be flowing?
No current.
No current. So 0, 0 should be one of our data points, right?
Yeah.
So then the next data point is going to be, we said there was 10 volts on the battery, and we saw there was a current of 1 amp, right?
Yeah.
So I've got that data point in. Now what Ohm would have done would have been increase the voltage a little bit. Let's say we went to 12 volts.
Okay.
So if I increase the voltage right now, what's going to happen to the current reading?
It'll go up.
That's exactly right. So I'm increasing it from 10 to 12 volts, and it now says, notice 1.2 amps, right?
Yeah.
So now I would go back to my data set and put when there was 12 volts, we had 1.2. Now we go back here. Let's increase it from up to, let's say, 14 volts. More voltage, more current, right? And remember what we said in our the last meeting was that one of the basic ideas that Ohm had uncovered was that voltage was proportional to current. Remember that?
Yeah.
And that's what I'm writing here. And are we seeing evidence of that right now?
Yes, we are.
Yeah, more voltage in the battery, that you end up with more current, right? It means also that if they're directly proportional, that means, and they're linear, meaning they're both raised to the first power, that means if you double your voltage, what should happen to your current?
Your current would also double.
Exactly. That would mean that they're both V raised to directly proportional. It means V raised to the 1 power is proportional to I raised to the 1 power. And so let's go back, and I'm only going to do a couple more of these, but you'll get the point. We did, 16 volts on the battery. You can probably already see that there's a pattern. Now you get 1.6 amps, right?
Yeah.
So let's just stick with Let's just stick with that. That's enough. So we had when there was 14 volts, we had 1.4 amps. And then when there was, our last data point was 16 volts, we got 1.6 amps. So Ohm was, of course, a scientist, physicist, mathematician. I don't know if you call him a mathematician, but certainly skilled in mathematics. So what would his next step be after he had his data set? Because he's trying to find out if there's a correlation. Creates a data set, what would he do next? What can we do with our data set? That's a good guess, but he doesn't know the formula yet because he hasn't invented the formula yet. His goal is to try to find a pattern and then create a formula that can be used to model that pattern. So what we're going to do next is graph our data. Right?
Yeah.
So what do you think the shape of our graph is going to be? And if you look at that data.
Like a diagonal.
All right.
Line.
Yeah, that's a good guess. Let's see what we get. So I'm going to go ahead and insert. Let me move this a little bit over to here. Over here. Insert. Graph. So the kind that we use in science called a scatter plot?
Yeah.
Okay. All right, so let's expand it a little bit. Oops. All right, so what shape are we seeing?
A diagonal line.
Yep, a diagonal line. And one moment, this would be called voltage versus current. On our x-axis, we have current. Which is measured in amps. And then on our y-axis, we have our voltage measured in volts. All right?
Yeah.
All right, so you see that now. So now, if we wanted to get an equation that models this data, how would we do that? So let's just go back now to my drawing pad here. So now, where's that? Let me go ahead and move this back to this side of the screen. Move this back up. I'm going to erase this board now. Okay, and so now you find that you have yourself a graph of voltage versus current, right? And we saw that it was linear. So to make create a mathematical model, which is called an equation, for this data set, we would think back to our algebra skills and think, what are some of the formulas that we learned in algebra class? Well, what's the one that's the model for any linear graph in terms of y's and x's?
Yx squared.
That's a good guess. So, like, if there was a proportional to x, if y was proportional to x squared, then it would be a parabola.
Yeah.
But we're seeing that when y is proportional to x, when they're both raised to the 1 power, it creates a straight line, right? Because we just saw that. We collected data and saw it made a nice straight line, right?
Yeah.
So what is the formula from math class? Y equals m.
Y equals mx plus b.
Yes, y equals mx plus b, right?
Yeah.
So I'm stepping you through the steps that Ohm would have done to create his law. So what is on our vertical axis? On our graph, which quantity did we put on the vertical axis?
Oh, voltage.
Yep. So instead of y, we put v for voltage, right?
Mm-hmm.
What quantity do we put on our x-axis? capital I stands for current. Yep, current in amps. And then V stands for voltage, measured in volts, right? So on our x-axis, which quantity do we have?
On our x-axis, we have
current. So I'm going to put the symbol I there. See what I'm doing?
Yeah.
What is this thing called B in math class here at the end of y equals mx plus b? What is that B thing?
Y-intercept.
What was our y-intercept from our data? Yeah, it's exactly. It's 0. I don't mind showing you again. Go back here. You see, if I tell it to give me a fit, add me a trend line. You see it now?
Yeah.
Right through the right through the origin, 0, 0, right?
Yeah.
And that makes sense again because 0 volts. You have a dead battery. It won't create any current. 0 amps, right?
Yep.
Okay. So now we go back to our modeling exercise. And what number should we stick in for B in y equals mx plus b? 0, exactly, because that data point was 0, 0, right?
Yep.
And so the very last thing is to recognize that this slope here, m is the slope, right?
Yep.
And so if I want to show you something here, if I go back to this thing, do you notice that it shows that it's a 10 ohm resistor?
Yeah.
Notice, let me see if I can, hold on a second. So do you see how the resistor in this simulation shows that it's 10 ohms? Right above it says the number 10.
Yeah.
So that was a 10 ohm resistor, right?
Yeah.
Okay, so let's go back to our graph on Excel, which is right here, and let's ask Excel to give us an equation of best fit. Are you familiar with an equation of what that means? An equation of best fit?
An equation
of best fit. So an equation of best fit is an equation that fits the data set that you've put on the graph.
Okay.
So this really shouldn't be here because this last piece, E means 10 to the something, right? 10 raised to the some power.
Mm-hmm.
And it's saying E minus 15, that's 10 to the minus 15. Is that a number very close to 0?
Yeah.
So technically that should have been the number 0 because we already knew the y-intercept was 0, right?
Yeah.
So what is this showing us? Well, it's giving us a linear graph, a linear equation, y equals mx plus b, right?
Yep.
And we already said what was our y-axis? What quantity was on the vertical axis? Voltage. So I'm going to erase it and put V. What should I put in place of X? Current. And now, oh, look what that number is in front of that symbol, I. It's called the coefficient. What number is that? The coefficient to the I variable.
Must be in there.
It's okay. See how it says V equals 10I plus 0?
Oh, okay.
So the coefficient is the number 10, right?
Yeah.
So let's go back to our simulation. What is the resistance of that resistor? 10. So what does that tell us about our model that we're creating?
That the resistor is the coefficient?
Yes, very good. It tells us that V equals something that we didn't know what it was times the current, right? V equals something I. So we go back to here. Oops. We go back to here. What is M? In math class was called the slope. Well, what is that thing 10? 10 represented the what in that circuit?
The resistance.
The resistance, see? That means this is really R, right?
Yeah.
And that is Ohm's law. It's just not normally written V equals R times I. It's normally written V equals I times R. But it doesn't matter which way you order it. It's just two things multiplied together, I and R or R times I, right?
Yeah.
And that is Ohm's law. That is Ohm's law. So Ohm's law is a law that shows that voltage is directly proportional to current. In fact, let me erase some of this. So what Ohm's law is showing is that, I should have said current is directly proportional to voltage. Is proportional to voltage. So what that means is if we double the voltage, will we double the current?
Yeah.
Yeah, well, let's go check on our simulation. It's currently 16 volts with 1.6 amps. If I double the voltage from 16 volts to 32 volts, what will the new current reading say?
32, it's currently 15 to 10.
Yep, I'm doubling the voltage from 16 volts to 32 volts. What will the new current reading say?
20.
What does the current reading currently say?
10.
No, you're looking at the voltmeter. Remember where that little box is inside? It says 1.6 amps.
Yeah.
So what will that new value say when once I double the voltage on the battery?
It's going to be 2. It's going to be 3.2.
Can you see it?
Yeah.
Right? So it's showing that a doubling of voltage produces a doubling of the current, right?
Yeah.
All right, so back to here. So that's what this first big idea is that Ohm had discovered. And then he also had realized something else, which I haven't shown you yet. What's going to happen to the voltage? I'm sorry, I didn't mean to say that. What is going to happen to the current, which currently says 3.2 amps? What's going to happen to that number if I increase the resistance of the resistor?
What's going to happen to the voltage if you increase the number of the resistor?
So I'm going to leave the voltage the same on the battery. It's currently at a 32 volt battery, and I'm going to leave it that way.
Okay.
And we currently have a 10 ohm resistor and 3.2 amps of current in the circuit. What I'm going to do is I'm going to make the resistor have more resistance, some number greater than 10. What will happen to the number for current, which is currently 3.2 amps? Will the value there go up to be a number greater than 3.2? Will the number stay 3.2, or will the number become less than 3.2 amps if I increase the resistance of the resistor?
It would be less than 3.2 amps.
Good, it would be, because those two things, current and resistance, are directly proportional or inversely proportional?
Directly proportional. Not inversely proportional.
Good, inversely proportional. Yep. Because more resistance should do what to the current? Make it more or less?
Less.
Less. Yep. So if I go back to here, what you're claiming is correct, which is that current is inversely proportional to resistance, right?
Yes.
So that means, in words, current is inversely proportional to resistance. Now, if we're going to think to ourselves, if these are both implied to be raised to the first power, if R is to the first power and I is to the first power, that means if I double the resistance, what should happen to the current?
Also, it would decrease
By what factor if you double the resistance?
by a factor of 2.
Exactly. It should so when you increase the resistance by a factor of 2, meaning doubling the resistance, the current will decrease by a factor of 2, which means it should cut in half, right?
Yeah.
Because more resistance always equates to less current. So let's go back to the simulation and see if that's true. I'm going to change the resistance from 10 ohms to 20 ohms. What is the new current reading going to say on the amp meter?
Yeah, so the 10 ohms to 20 ohms is going to be 16.
It's current. You're looking at the volt.
If you increase it.
Yeah, so I just wanted to point out this black box here. This is just measuring the voltage of the battery, and I'm not changing that at all. But the white box on the left, that's our amp meter, and it says 1.6 amps. So it's currently 1.6 amps, and it's currently a 10 ohm resistor. But what I'm going to do is change the resistor from 10 ohms up to 20 ohms. What will the new value be on that white box? Well, if I double the resistance, what did you tell me? You told me that the current will cut in half, right?
Yeah.
Well, what is half of 1.6 amps?
1.6 amps is 8.8.
Let's see. So I'm doubling it to a 20 ohm resistor, and what do we get? Oops, all right, that didn't work. Try again. Oh, is it currently? Oh, I'm sorry, I take it back. We were originally at 3.2 amps in our last iteration. And let me put these values back. So before it was a 10 ohm resistor and it was 3.2 amps. And so now when I double the resistance, it's going to cut in half from 3.2 down to 1.6, right?
Gotcha.
So now I'm doubling it from 10 to 20. And as soon as I do that, it cuts down in half to 1.6 amps, right?
Yeah, I see.
All right, so that kind of finalizes and finishes off Ohm's law. He showed that the first part up on top of the screen, he showed that current and voltage were proportional and that they were linear to each other, meaning both raised to the first power. That means if you double voltage, you'll double the current. If you triple voltage, you'll triple the current. If you increase voltage by a factor of 2.7, current will go up by a factor of 2.7. That makes sense?
Yeah.
And then the last part is this bottom part showing that current was inversely proportional to resistance, right?
Yeah.
And so when we merge these two ideas to create an equation, what would we get? We'd get I equals, what would this be now in terms of a ratio over here?
1 divided by R.
Close, but remember I was proportional to V. So where would it go in this fraction, in the top or the bottom, if I is proportional to V?
I is proportional.
So would V go on the top of this box I'm going to fill in here, or would V go on the bottom?
The top, yeah.
On the top, right?
Yes.
And then what will go on the bottom?
R.
That's correct. And so when you cross multiply, if you imagine this was I divided by 1, so if I now take I and let's say, oh, well, let's just draw it as something over 1, and then cross multiply, what do we get? V times 1 is V, and then I times R is IR. Isn't that Ohm's law again? You see that?
Yes.
That is Ohm's law. So I've shown you two different ways of looking at it all, which all say that voltage is equal to the product of current and resistance, and more conceptually that current and voltage are directly proportional, and current and resistance are inversely proportional. All right?
Yes.
All right.
Yes.
All right, so now moving on. Let me look at one of your problems. Okay. So now what we're going to do is we're going to go back to our simulation. And I'm going to make these normal numbers. Let's make it like a 10 volt battery. And then we're going to make this resistor, I don't know, like 2 ohms. So, in fact, let's remove this. Why don't you go ahead and just use Ohm's law right now to just do a quick practice and check in to make sure you get this.
Okay.
So I'm going to make the resistance, let's make it 5 ohms. So the resistance of the resistor right now is 5 ohms, and the voltage is 10 volts. How much current should flow in the circuit? The resistance of the resistor is 5 ohms, and the voltage on the battery is 10 volts. How much current should we get in the circuit?
The
So if we go back to this screen, remember that I is equal to V divided by R, right? So I'm just having you use Ohm's law now in this example just to make sure you're getting that. So I, the current, is always the voltage divided by the resistance.
Yep.
And so our voltage we said was going to be 10 volts, right? And our resistance was going to be 5 ohms, right? So we go back to here. There's a 10 volt battery and a 5 ohm resistor. So how much current should we get? 10 divided by 5 is 2 amps, right?
Yeah.
So we go back to our simulation. Not sure why it's not running right now. I paused it by mistake. Here it goes. And so now, do this one more time. This is reading how much current there is. You see what it's showing?
Yeah.
2 amps, right?
Yeah.
All right. So now the question is, what if I add more resistors to the circuit? What if I decide to split this open and add another 5 ohm resistor right here next to it? That's called putting these resistors in series, because series means one after the next, right?
Yep.
So let's just say they're both 5 ohm resistors. Circuit. And we're going to just connect them the way we had before, just right up to the circuit like this. So what do you think would happen to, remember before we had 2 amps just a moment ago, remember? When I connected it, it's still going to be 2 amps now that we have a second 5 ohm resistor in there? Or are they going to be more than 2 amps or less than 2 amps?
It would be less than 2 amps.
Because?
We have more resistance.
Exactly. Notice we actually have 1 amp now, right?
Yeah.
So guess what the total resistance of the circuit is right now? Let me actually, yeah, give me 1 second. I'm actually going to try to make this larger so it's easier for you to see, because I have a feeling it's kind of small. So let me see if I can make this better. Let's go like that. Let's move this over to large. That's a little better. That's a lot better. I'm saying. So,
Thank you.
yeah, I'm sorry if that it was tiny. The only downfall is that I don't know if I'm going to. Small. All right. So can you see all that now? Better?
Yeah.
All right. So guess what the total resistance of the circuit is when you put 2 5 ohm resistors into the circuit? 10 ohms, right? Notice we have, remember, current is always voltage divided by total resistance, right? So what is our voltage? 10 volts. What is our total resistance? We've got 2 5 ohm resistors in there. 10. So what is 10 divided by 10?
0.
10 divided by 10?
1.
1. And that's why we get 1 amp. So I'm pointing out that Ohm's law always works. It doesn't matter how many resistors you put in there. Right? What if we decide to put a third one in? Now I'm going to put a third, let's just say it's a, I don't know, 10 ohm resistor. What is the total resistance now? Because now we have, let me make this a little clearer. Sorry, give me a second. All right, so what is our total resistance now? What is it?
20 ohms.
20. It's 10 plus 5 plus 5, right? So what is the total current going to be?
5 plus 5%.
So the total resistance is 10 plus 5 plus 5, which is 20 ohms, right?
Yeah, yeah.
So I added up, that last one I added in there was a 10 ohm resistor, and then we've got a 5 and a 5. So we had a total resistance of 20 ohms. The battery is still 10 volts, so what should our current be now? Still 1 amp like it was before with just the two 5 ohm resistors, or more than 1 amp or less than 1 amp now that I added a 10 ohm resistor?
Less than 1 amp.
Less than 1 amp. And what specifically should we get for the current? Use Ohm's law. I is V divided by R.
10 divided by 20.
Yep, what is 10 divided by 20?
0.5.
0.5. So if I move this over, as you watch on the screen, see how much current there is?
Yeah.
0.5. So what we've uncovered is a new law, a new rule. And I'll write it down for you in the notes here. Just going to erase this board. And so what we found is a rule, and it applies to series circuits. That the total resistance of the circuit is equal to the sum of all of the resistors. So what that means is it's equal to R1 plus R2 plus R3 plus however many resistors you have. So in this example that we were just doing, R1, let's say, was 10 ohms, R2 was 5 ohms, and lastly R3 was also a 5 ohm resistor. Then what's called the total resistance is the sum of all of those, right? 10 plus 5 plus 5 is 20 ohms, right?
Yeah.
So that idea applies to all series circuits. When there's one continual loop that goes round and round and round for the electricity, you just add up all the resistances to get the total resistance. All right?
Yeah.
So now we're going to go back. So if I decided I wanted to take away all three resistors and just put one resistor in, but I want it so that the current doesn't change. I want it to still be 0.5 amps. So again, this is an engineering problem. We've got three resistors. We want to cut down our costs because, for example, putting three resistors into every computer, so we'd like to put one resistor in here, and we still want it to be a half an amp flowing in the circuit. What would I do to solve that problem? What resistor would I put?
You wouldn't be able to put 3 resistors in there, but still have half an amp flowing.
Yeah, I still want the current to be exactly the same, and it's still going to be 10 volts. But we want to get rid of 3 resistors and insert only one resistor into the circuit so that we still get a half amp. What would I do?
Change it to 15 ohms. Let me change the one resistor to 15 ohms.
I'm sorry, what's the question?
You change one resistor to 20 ohms, I mean?
Exactly. So you're saying put one resistor in that has what resistance?
20 ohms.
20 ohms. So let's go do that. We're going to remove this one. We're going to remove this one. And now I'm going to change this one single resistor to a resistance of 20. And cross our fingers, but we don't have to because we know we did our math. And Ohm's law is correct. And now it's got one resistor of 20 ohms. When we close the circuit, how much current do we get?
We'll still have the same amount of current.
Do you see that it still is on the screen, a half amp?
Yeah, half an amp.
Yeah. So what I'm showing you is, in your textbook, they call that the equivalent resistance.
Yeah. All right, thank you.
Are you still there, Jeremiah?
Yeah.
Okay. So what they call in your textbook, they call it the equivalent resistance, and they normally just write REQ.
Okay.
Is the idea that we just talked about, that you can take away three 5-ohm resistors. Oops, sorry. In a series circuit and replace them with one. How much resistance would this have? Of equivalent resistances, you can take away 3 5-ohm resistors in a series circuit and replace them with 1 watt-ohm resistance to have the same circuit. What is the total resistance or equivalent resistance of 3 5-ohm resistors in a series circuit?
15 ohm.
Yeah. So this is the idea that you can take them away and replace them with 1 15-ohm resistor and still have the same current. And still have the equivalent, I'll use that word, total resistance and current, right? Those didn't change. So the idea is that you can take multiple resistors away and put one in its place so that the total resistance is still the same and the current doesn't have any effect, on the current. That idea is called equivalent resistance, and they use that in your textbook. They call it R sub EQ. All right? And so in your textbook, if you read that and you see R EQ with an S, or that this EQ stands for, again, equivalent, and then S stands for series. Other times, like on the AP exam, they don't do that. They just put RS equals, and they'll show on the AP exam equation sheet that you get, it'll show the sum symbol the way I had shown with you. It shows it a sum of RI, and that just means the sum of them all. R1 plus R2 plus however many you have, right? But just know that whenever anybody says equivalent resistance, that's the idea. That you can just add all the resistances up and figure out what is the equivalent that you could stick in its place to have the same total resistance. All right, any questions on that? No. All right, so the very last part, so that you can finally do number 2 of your homework, is the idea that all things have resistance, okay? Physically, there's nothing in our universe that we found exactly 0 resistance to electricity flowing through them. Everything has some resistance, but they all have different amounts of resistance. Things that are metals are conductors, they have low resistance. Things that are insulators like rubber, plastic, wood, styrofoam, those are all insulators. Those have a very high resistance, right? But the point being, all things have resistance. We've never found a single thing that you can try to push electricity through and find that there's no resistance to pushing it through. And so it turns out that batteries themselves have resistance because the electricity occurs because you have 2 plates on each side of your battery. Picture of that. This is a close-up view of a battery. You have a plate in here, and you have a plate in here that will have opposite charges all piled onto them. This might be all negative charge over here, and this is, let's say, all positive charge. And it turns out that the electricity that's all stored up, the charge Q that's all stored up on this plate, has to flow through the material that's in here. And this area still has resistance. Because the charge has to leave that plate and flow through the battery. So this area has resistance. Right?
Yeah.
And so it turns out that, let's just say we had a battery in my picture and then a 5 ohm resistor connected to another 5 ohm resistor. And then we, based on what I'm telling you now, is, oh, the battery itself has a little bit of resistance. Maybe it's 1 ohm. What is the total resistance of this circuit that I've just drawn for you? Based on this picture I've just drawn on the bottom left of the screen, showing that there's 2 resistors that have 5 ohm resistance, a resistance of 5 ohms. And so this right here is a resistor, and this right here is also a resistor. And this right here is your battery. And I'm pointing out that the battery itself has some resistance, and I'm saying it's 1 ohm resistance based on this picture I've just shown you on the right. And so in the real world, if someone said, what is the total resistance of this circuit, what would it be? 5 plus 5 is 10, that's it?
No.
What would it be?
It would be 5 plus 5 plus 1.
Exactly.
That's the battery. Oh.
Yeah.
It would just be 5 plus 5.
5 plus 5 plus 1, like you told me, because the battery itself has some resistance of 1 ohm. And so it would be 5 plus 5 plus 1. So the total resistance of the whole entire circuit is really 11 ohms.
Oh.
Because the battery itself adds some resistance to the circuit.
Yeah,
And then what I would even tell you is that cables that we've used to connect all these, do those have 0 resistance?
Do those have what?
Do the cables themselves that we're showing here, right here, do those cables have 0 resistance?
No.
No, everything has some resistance. You might find out that this cable has a 0.5 ohm of resistance, that this cable has a 0.5 ohm resistance, and the cable over here has a 0.5 ohm resistance. So in the real world, electrical engineers and electricians all have to consider this. What would really, in my new picture, what would really be the total resistance of this circuit?
It would be, what's that, 25? 25?
So it's 5 plus 5 gave us 10. That came from our original.
25 or 25?
Those are 0.5. I know that's messy. So each. So you'd have.
Okay. There's the, 25. That's about 1.5. So it's like 12.5?
Yep, exactly. So you'd have 5 and 5, which is 10 ohms, comes from your resistors. Then you'd say, oh, there's an extra 1 ohm of resistance inside of our battery that gives us 10 plus 1 is 11. And then you'd say, oh, we got 3 cables in there that all have a 0.5 ohm each, which provides another 1.5. So the 11 plus 1.5, we'd say, okay, the total resistance is really 12.5 ohms, right? And so when you are using Ohm's law, V equals IR, R is the total resistance of the circuit, and you'd have to include everything inside the circuit that has a resistance, and you just add them all up.
Yeah, gotcha.
Okay, but again, that idea of adding them all up only applies for a series circuit. Once we start talking about parallel circuits, it turns out there's a little bit of a different rule. But with that being said, why don't you give number 2 a try on your homework? Oh, there's one idea. Sorry, you're not ready just yet for it.
Okay.
So let me go, but this will only take a second to show you. If we go back to my my app here, which is not working. There it goes. So if we go back here, notice that the voltmeter says 10 volts. Jeremiah?
Yeah, I see it.
So the voltmeter says 10 volts. What if I take another battery that has, this is now a 9 volt battery, and I stick it end to end like we do sometimes in our remote controls? What will the total voltage of them together be?
19.
Yeah, you just add them. So when you stick batteries end to end like that, their voltages just add.
Yeah.
All right? That's all I need to show you. Because in number 2, your homework problem, notice it says 4 1.5 volt cells. When they say cells, they're referring to batteries, are connected in series. And what I'm showing you in this picture on the app is that those 2 batteries are in series, just series means one after the next, right? And you're seeing that the voltages add. So with all that I've said, I think you're ready to try number 2. Ooh. And the one vocab word that I didn't tell you is that when I told you that all batteries have resistance, they call that internal resistance, because remember the picture I showed you was that resistance comes from the electrons on one plate traveling through the middle of the battery to the other side.
Yeah.
And that's internal to the battery, so they call it internal resistance.
Okay. Go first.
So step me through what you're thinking right now.
Alright, so first I found the total voltage in the battery. Then next I wanted to find the total resistance.
Well, let's start on that first step. So you said you wanted to find the total You said you wanted to find the total voltage of the 4 batteries. What would that be? I think the total voltage of the 4 batteries. What would that be?
Yeah, that came up to 6 volts.
Yep. And so there technically would be another formula, which is the total voltage in series is the sum of all of the voltages, which would be, plus, which would just be, so when you see that sort of notation in a math class or in physics, again, the sigma symbol just means to add up, right?
Yeah.
So it would just be equal to V1 plus V2 plus V3 plus however many voltages you have because of the different amount of batteries. So you said that would be, 1.5 plus 1.5 plus 1.5 plus 1.5, which we know is just 1.5 times 4, which would be 6 volts, right?
Yeah.
All right, so that's true. Got a 6 volt, and that's called a battery pack. When you take small batteries and you put them all together to make a larger voltage, that's called a battery pack.
Got it, yeah.
All right, so you got a 6 volt battery pack. So what's your next line of thought?
And next I want to find the total resistance.
Okay, how will you find the total resistance?
By adding the resistance of a light bulb and multiplying it by the resistance of the 4 batteries.
We don't know the resistance of the 4 batteries yet.
Yeah, that's what we're trying to find.
Yeah.
That's what I'm trying to find.
That's right.
So, and then by knowing that's what I'm trying to find, I then use Ohm's formula.
Good. Ohm's law, which is normally V equals IR. So what will we do with that? How will we use that?
I plugged in the total voltage.
Yep.
The amp. And I multiplied it by 12 ohms. I'll add that to 4 times how many resistance of the internal batteries are.
All right. So when we use this now and solve, I think everything you said was right. When we use this now and solve for where's my pen? I can't see where it is on the screen. Give me a second. Oh, there it is. When we use this to solve for the total resistance of the circuit, it will be the voltage of the battery divided by the current that we are observing, right?
Mm-hmm.
And what was the voltage of the battery pack? You said it was 6 volts, right?
Yes.
Divided by what current are we observing? It says 0.45, right?
Yes.
So what is 6 divided by 0.45? Let's see. Oh. 13.33.
13.33?
Or 13.34, yep. 13.34 ohms. That's the total resistance of everything, right?
Yeah.
How much is coming from our light bulb? How much of that 13.34 ohms, which is the total resistance of the bulb and the batteries, how much of that 13.34 ohms is coming just from the light bulb?
0.45.
That's the current that's flowing through the circuit. So just read through the problem. Yep. So out of the 13.34 total amount of ohms, 12 of those ohms are coming from our light bulb, right? So how much must be coming from our batteries?
Out of 13.
So the total resistance we found was 13.34. And that is our 12 ohm resistor that they've described in this problem. Because notice they said, I didn't mean resistor, but our 12 ohm light bulb they described.
Mm-hmm.
They said that there's a light bulb that has a resistance of 12 ohms. And we know we've got batteries that also have some resistance, right?
Yes.
So the total amount that we found is the 12 ohms plus resistance of batteries, right?
Yeah.
And that total amount comes out as 13.34. Remembering that the 12 comes from the bulb, right?
Yeah.
So how much if the 12 ohms from the bulb plus some unknown amount of resistance from our batteries equals 13.34, how much is the resistance from the batteries?
1.34.
Yeah, exactly. 1.34. And you certainly could have, if you wanted to, is represent that idea mathematically. You would say that the total resistance of circuit is equivalent to the resistance of the bulb plus the resistance of the 4 batteries, right?
Yeah.
And so the total resistance of the circuit we know is 13.34, right?
Yeah.
And then the resistance of the bulb they told us was 12. And so our unknown resistance for 4 batteries, we would just subtract both to 12 to both sides, right?
Mm-hmm.
And what would we get? As you told me, it'd be 13.3 minus 12 is 1.34 ohms, right?
Yeah.
And that's the total amount of resistance for 4 batteries. Notice they ask, what is the internal resistance of each cell?
Got it. Yeah. And that's what you're trying to find next by using Ohm's law.
No. 1.34 ohms of resistance for 4 batteries. Remember, we created a battery. And remember that the resistances add up in series, remember?
Yeah.
So if you get 1.34 ohms of resistance for 4 batteries that are stuck together, what is the resistance of just one of the batteries? You got to divide it by 4. Very good, yep.
I got 20.335.
You got it, yep. So you would take the resistance of 4 batteries, which was 1.34 ohms, and divide by 4 batteries. And notice the units will be ohms per 1 battery, right?
Yep.
So you end up with 0. What did we just say? 335 ohms per. We always just write the answer is 0.335, but it really means per 1 battery, right?
Yep.
And that's what they asked. They call a battery a cell. All right? Good on that one?
There we go.
All right. Notice, what did they assume was negligible in this problem, number 2? You read through it. What did they say right at the end? It says, assuming they are
identical
and
the resistance of wire.
right. Assuming that the wires have no resistance. In the real world, is that true?
No.
No. In the real world, those cables and wires do have some resistance. So in the real world, would it still be 0.45 amps flowing in the circuit? More than 0.45 amps or less than 0.45 amps?
More.
If you have to consider remember, it would be less, exactly. Because if you are considering the idea that there is some resistance in the cables, that's going to make the total resistance go up or down? Up. And so that would make the current go down because those are inversely proportional, right? Good. All right. Let's check on your next one. All right. You only need to learn a little bit. I taught you a lot, I think. And from here, I just have to teach you little bits that just add on to what I've already taught you. All right, so I'm going to go to the next idea, which is actually a pretty quick it's a pretty quick idea to show you, and I think you'll be able to use it. So let me go back to my simulation and look at what I'm simulating. A 650 ohm and a 1800 ohm resistor are connected in series with a 12 volt battery. What is the voltage across the 18 ohm resistor? Okay, 650 and 18 ohm. So let's see. So I'm going to make this 650, and then the other one was, oh, I can't go that high. Shoot. I'll just make a similar problem, and then you'll try number 4. All right, so let's, in that problem, they only have 1 battery, so let's remove one of the batteries. Let's make it a nice, easy number, like 10 volts versus 9 volts, or let's say 20 volts. And then We have to add one more resistor because they gave you now a problem with 2 resistors. That's easy. Just add another resistor here. All right. So notice we now have 2 resistors in series with each other, one after the next, a 20 ohm and a 10 ohm, right? And then we have a voltage on the battery of 20 volts. So to answer their kind of question, which is how much voltage is being used on one of the resistors, I have to teach you this idea that is technically known as Kirchhoff's law. And so I'll write that down in the notes. This is referred to as Kirchhoff's law. The total voltage drop across all areas of resistance in a circuit is equal to the voltage of the battery. So in simple terms, that's what you'd find similar to that in a textbook, but it doesn't always necessarily make perfect sense when you read things from a textbook. So I'm going to teach you, I'm going to come back to this, but I'll teach you in simple terms so it makes sense. So let's go back to our thing here. And so what that means, what Kirchhoff's law is saying is that when you have a 20-volt battery like I have, the battery has to use all of its voltage to push electricity through the areas that have resistance. And you can kind of think of voltage as, because voltage is really a collection of electrons that are inside of the battery, right? And they don't want to be next to each other and all piled up on that plate. They repel. Coulomb's law says electrons repel electrons, right? Yeah. And so when you give them a path to get off that plate and start flowing through a circuit, they're going to take it because they're in a very high energy state, all piled up on a metal plate next to each other, very close. And that's the idea of voltage, is that it's the collection of similar charges in a small space. And so when they push, because repelling is a push, right? That's a force. Repel, they're pushing each other apart. And that pushing force is what allows them to push themselves through all the areas that are high resistance in the circuit. So think of this 20 volts as a total amount of pushing force. Again, it's not a perfect analogy because voltage is not equivalent to a force, but I'm just trying to have you build this idea. Think of 20 volts as an ability to push charge through the high resistance areas, and the battery has to use all 20 volts. That's what Kirchhoff's law says. And so it can't save some of that voltage for some other time. When it's connected in the circuit the way we're seeing, it has to use all 20 volts at any given moment. So let me change the resistance of this to, let's say, 10 ohms. So now we have 2 10-ohm resistances. If we go test how much of the 20 volts is being used to push electricity through this resistor, I would take my voltmeter and test it, one on each side, and it's telling me, out of the 20 volts that this battery is using to push electricity through these high resistance areas, which are the resistors are high resistance areas, out of the 20 volts available, it's using 10 of those volts to get through this resistor. Guess how much it's going to be using to get through the other resistor? 10. Because it has to use all 20, and it's using 10 here. And if you go test this other one, it's using the remaining 10 here. I know that shows negative just because I switched the leads. It shows another 10 is being used here. And those two add up to what amount? 20, which is the voltage of the battery, right? So the idea that the battery is using some of its voltage to push through this resistor is called a voltage drop. To drop means to be decreased by. So the voltage in this area of the circuit over here is 20 volts. And then as you continue along here like this, see how the voltage drops when I go from here to here? So this side over here, the red side, is the 20-volt side of the battery. And this, again, the simulation assumes that the cables have no resistance. So as I test and move this black slide along, there's no change in the voltage. It says still 20. But as soon as I go across this resistor, the value is going to drop from 20 to 10. You see that?
Yeah.
So they call that a voltage drop. Because where is that voltage being used? To push through that part of the resistor. Right?
Yeah, I see.
And then once I trace along here, notice it's still 10, 10, 10, 10. What's going to happen when I get to the other side of this resistor? What is it going to drop to?
0.
0. See? Because it used its last 10 volts to push through this second resistor. It dropped again by 10 volts. Right?
Yep.
And so Kirchhoff's law is the idea that the total voltage drop around all parts of your circuit, how much voltage drop is here? 10 volts. How much voltage drop is on this other area? 10 volts. That those have to add up to the total voltage of the battery, which is 20, right? And 10 plus 10 is 20. Kirchhoff's law, the total voltage drop across all areas of resistance in a circuit is equal to the voltage of the battery.
Gotcha.
Right? And so the key idea is that a battery, when it's in a circuit, it always is using all of its voltage to push electricity through all of the different areas. It can't save some for some other time. It has to use all of it.
Okay.
It happens to be that it was an equal 10 volts, a voltage drop of 10 volts here, equal to this amount over here, only for one particular reason. Because if I bring up these values again, what are the values of those resistances when you compare them?
Values.
The resistances themselves of the resistors are both 10 ohms, right?
Yeah.
And so it's using equivalent voltage because it's equally difficult to get through the first resistor as it is to get through the next resistor. And so it uses equal amounts, 10 volts, to get through each because it's the same difficulty to get through both, right?
Yeah.
What if this was now a 20 ohm resistor, though, and the other one stays a 10 ohm resistor? Will the voltage drop still be 10 and 10? This is now a 20 ohm resistor that I've put here on the top, 20 ohm resistor on the top, and a 10 ohm resistor on the left. When I go measure those voltage drops, will it still be 10 and 10? Well, who is going to be hardest to get through, the 20 ohm or the 10 ohm?
20 ohm.
20 ohm will be harder to get through. So should it use more voltage to get through the 20 ohm, I meant? Should it be using more of its 20 volts that it has available? Should it be using more to get through the 20 ohm resistor or more to get through the 10 ohm resistor? More to get through the 20 ohm. Let's go see how much it's using. 13.33 now. How much will it be using on the 10 ohm? Remember Kirchhoff's law.
7.
Yep, about 7. Let's go test it. 6.67, but you got it, right? You get the idea. And again, it's only negative because I keep forgetting to reverse these. And what does this 6.67 plus the voltage drop on this one, 13.33, what do those add up to? 20. That's Kirchhoff's law again, right?
Yep.
And so why is it using more voltage on the 20 ohm compared to how much voltage drop there was on the 10 ohm? Because there's more what in the 20 ohm? More resistance, exactly. So in a series circuit, the battery will always use proportionally more of its voltage to push the current through high resistance areas because it's hard to get through, so it has to push harder to get it through. And it will always use less of that voltage available to push through areas of less resistance because 10 ohms is less than 20 ohms. But again, they always have to add up to the voltage of the battery. That's his law, Kirchhoff's law, and since it's called a law, it means it's always true. All right? All right. Now, I've taught you the ideas. How can we use math to predict that the voltage drop on this guy is 6.67 volts? Well, first, we would have to be able to predict how much current is flowing in our circuit. So what is the total resistance of my circuit right now? Again, this app, this simulation assumes that the cables have no resistance. And I've got a 20 ohm resistor and a 10 ohm resistor. What's the total resistance of the circuit?
30.
What is it?
30.
30, yep. 20 plus 10 is 30 ohms. Again, it also assumes, notice it says 20 volts and then 0 ohms here next to the battery. It's assuming that the battery has no internal resistance, and it's assuming the cables have no resistance.
Okay.
Not true in the real world, but it's just an assumption. So total resistance would be 30 ohms. What is the voltage of our battery? 20 volts. So how much current should be in our circuit right now?
20 volts.
How much current should be flowing in the circuit? Let's go back to our drawings. Remember, Ohm's law is that the current is equal to the voltage divided by the total resistance. And so our total, our voltage on our battery is 20 volts, and our total resistance is 30 ohms, you said, right?
Yeah.
So if we do 20 divided by 30, that should be 0.66 amps, right?
Yeah.
So we just used Ohm's law to figure out that there should be 0.66 amps, and when I hover this over, it's rounding that to 0.67 amps, right?
Mm-hmm.
So now the point is, how can we predict, at this point moving forward, that the voltage drop on this resistor over here is 6.67? Well, the first thing you have to do is recognize that the current flowing through all parts of a series circuit is equal in all cases. So how much current is flowing out of the battery if you watch as I go around this loop? How much current is flowing out of the battery? 6.67 amps. I didn't mean 6.67. 0.67 amps. How much current is flowing in this section of the wire? 0.67 amps. How much current is flowing through this resistor here? 0.67 amps. How much current is flowing through this resistor over here? 0.67 amps. So the current is the same, and the current going through all of the devices inside your circuit is equal in all cases because it's only one path. So the total current has to go through all parts, and so it's equal everywhere. That's a really important idea. So let me write that one down. Because you pretty much get stuck solving a lot of physics problems in this topic if you don't know that idea. So that's why it's that important, that the current in a series circuit, the current going through all of the resistors or all of the light bulbs or whatever it could be. I mean, it could be a radio. It doesn't have to be a resistor. You can make a series circuit and plug a radio in there, and the radio will turn on. It could be a light bulb. It could be a heater. It could be a motor. It could be anything. All of those things can operate when the current flows through them, and they all have resistors. And you have a heater and a light bulb connected in a series circuit. However much current is going through the heater, the same amount of current will end up going through the light bulb. All right?
Yep.
So let's jot that down. Current, which is amps, flowing through all parts of a series circuit is the same. If multiple resistors are in circuit, the same current flows through all three. All right, does that make sense?
Yeah.
All right, so now let's go back to the simulation. How can we predict that the voltage drop on this resistor over here is 6.67 volts? Well, we get to just use Ohm's law again. This is the nice thing. Ohm's law is very useful. You can use it for the circuit as a whole by referencing the total voltage on the battery and the total resistance of the whole circuit and determine how much current is flowing around that circuit. Or you can take Ohm's law and just use it on one particular part of the circuit. So the voltage drop, V, that's being used on this resistor is going to be equal to how much current is flowing through this resistor times the resistance of this resistor.
Okay.
And so you'll see that this is really easy. What is the resistance of this resistor? You'll see it's a 10 ohm resistor, right? And how much current is flowing through it? 0.67 amps.
Gotcha.
So let's go over and show this idea that you can now use voltage V equals IR, that the voltage drop on a resistor is equal to the current flowing through resistor multiplied by the resistance of that resistor.
Okay.
Right?
Yeah.
So we're going to predict that the voltage drop is in fact 6.67 volts. And so let's do that. Let me trace a little bit of this, and then you'll be ready for your next homework problem. So how much current, again, going back, we had calculated, you can see it was rounded off to 0.67, and that's how much current's going through that resistor, right? So now we just go back here and say we're going to use Ohm's law, V equals IR, now just for that resistor to calculate the voltage drop, which should be the current flowing through that resistor multiplied by the resistance of that resistor. The current was 0.67 amps multiplied by what is the resistance of that resistor? It was a, I know it's a lot of stuff in the picture, but it was a 10 ohm. You see how it's a 10 ohm resistor, right? So now we just go back, we go back here and just say, okay, the resistance of that resistor is 10 ohms. So what is 0.67 times 10? 6.7 volts, right? And so we predicted using Ohm's law that the voltage drop on a particular resistor should be 6.7 volts. And you notice when we tested it, what are we getting? 6.67, just got rounded up to 6.7, right? Does that make sense?
Yes.
How could we have used it to predict how much voltage drop is on this 20 ohm resistor?
Say that again?
Could we also have used it to predict how much voltage was being dropped on the 20 ohm resistor?
Yes.
Yeah, it's the same method, right?
Yes.
So let's just show that. Go back one more time to here and show that had we done the same thing, I'm going to erase this. Had we done the same thing for that other resistor, the 20 ohm resistor, we could say the voltage drop on 20 ohm resistor is equal to how much current is flowing through the 20 ohm resistor multiplied by the resistance of the 20 ohm resistor, right? How much current was flowing through the 20 ohm resistor?
0.67?
Yeah, the same amount, because that's a rule. Same amount everywhere, right?
Yes.
So you go back here, you say, okay, I can do that. 0.67 times the resistance of a 20 ohm resistor, which is 20 ohms. And when you do that out, you're going to get 13.4 volts, right? And so then you go back to the picture, the app, and you go test it, and how much do you get? 13.33, which is rounded up to 13.4. You see that? And what do our two predictions add up to? They both have circles around them on the whiteboard. 13 point, they add up to 20, which is Kirchhoff's law, right?
Yes.
And notice, this is the last thing. This is the important idea. It used more voltage to get through the 20 ohm resistor, right?
Mm-hmm.
And it used less voltage to get through the 10 ohm resistor. By what factor was the voltage drop greater on the 20 ohm resistor compared to the 10 ohm resistor? Meaning, how many times bigger is 13?
That's so much bigger.
Give me an exact number, though. How many? What do you have to multiply 6.7 by to get the number 13.4? So 13.4 divided by 6.7 is 2.
Yeah.
Right? So
Yeah.
this is 2 times as much voltage twice as much voltage compared to this bit, right?
Mm-hmm.
Why did it use twice as much voltage?
Because there's exactly pushing.
Let's look at the resistance values. Why is it twice as much voltage up on the top right being used compared to down over here?
Because it is twice as much resistance.
You got it. That's the big idea. It has twice as much resistance. 20 ohms is twice as much as resistance as 10 ohms. So it uses twice as much voltage to get the same current through this one as it would have to push to get the same current through this one, right?
Yeah.
If the current has to be the same, the rate of electricity flowing through both of them has to be equal, and it's twice as hard to get through a certain section, then it has to push twice as hard. It has to use twice as much voltage to get the same current through that area. Does that all make sense? Because I think, if it does that make sense? Jeremiah?
Yes, it does.
All right, I think you're ready for number 4
Okay.
for your homework.
This could be a little simpler.
What's that?
So number 4 is a little simpler.
Can you try to bring the phone a little more to your mouth if possible?
That says number 4 is a lot more simpler.
Yeah, similar to the one we just did, right?
Yeah.
Yeah. That's why I wanted you to try it. Just different numbers. We can go on to another one if you want. It's up to you. I don't mind going on to the next one.
I know we can do it.
It's always best, I think, to try something all by yourself sometime after somebody shows you.
Mm-hmm.
I just want you to know that the language they're using, voltage across, is the same thing as voltage drop.
Okay. I got 8.8 volts.
All right, give me one moment. You got it. Good job. Excuse me. Thank you. All right, we're gonna move on.
Okay.
We have about 25 minutes left. I have to teach you what a parallel circuit is now.
Okay.
I'll try my best to squeeze it in. So let's go back over here. So there's a whole new way of wiring things. You don't have to wire them in series like we were just doing. Series means it's one loop, and the electricity has no choice at any point whether to go right or left. It's all forced in the same direction, right?
Yeah.
That's what a series circuit is. It's one continuous loop, no forks in the road.
Okay.
A parallel circuit has forks in the road. So let me show you what that looks like. Oh, that's annoying. So you see this?
Yeah.
This is a parallel circuit. So it turns out that if I were to make this equal resistances, both 10 ohm resistors, so this is actually going to take me a minute. I'm gonna try to make two circuits, one series and one parallel, so you can compare and contrast the differences.
Okay.
Because I feel like that's a pretty important moment when you're learning this topic, to see not just the mechanics of how to use the formula, because you can do that and then kids never really understand anything. But I want you to get the idea. So let's go like this. So I have two 10 ohm resistors on the right side that are connected in series. See that?
Mm-hmm.
And let's make the batteries voltages equal in both cases. So 20 volts. So on the right, we have a series circuit with a total voltage of 20 volts.
Yeah.
And then the battery on the left, also 20 volts. And then you notice, okay, how many resistors do we have on the left, which is the parallel circuit? Two 10 ohm resistors. How many resistors do we have on the right in series? Two 10 ohm resistors. We can see right away there's something different without even making measurements other than with our eyes. What can you tell is different with our eyes? You look back and forth between right and left side of the screen. What's different between these two circuits?
One half.
The parallel circuit has how many paths?
Two.
Yep, it has one right here, but then once they get to this point, which is called a node is when many different paths kind of merge together to form a single point. And so after the electricity reaches this point, it can split. Some of the electrons take the bottom path, and then the remaining bit of electrons take the top path. And then they all recombine back at this other node on the left side and form one continuous flow after that point. So that's true. You've got two paths here, series circuit, just one continuous path. What else can you see is different as you look back and forth? Related to the motion of those blue balls, and those blue balls are supposed to be electrons. Is one of the circuits moving electricity more quickly?
Yes.
Yes, which one?
Top one?
So we'll refer to the left circuit or the right circuit. In which one do you see the electricity moving a little bit more quickly?
Oh, the right circuit.
So it turns out that the left side right here is flowing very quickly. These blue balls are really moving along. But when you look at these blue balls over here, they're kind of just chugging along a bit slowly. See that?
They look like they're moving faster on my screen.
Oh, okay. So notice with my little amp meter, it's showing 4 amps is flowing on the left side, the left circuit. And how much current is flowing over on this side? Only 1 amp. You see that?
Okay. Yeah.
And then you'd wonder, how can that be? We have 2 batteries that are both 20 volts. And then we have the same amount of resistors in both circuits, 2. And they're, in all cases, they're 10 ohm resistors. So how can it be that we have way more current flowing on this parallel circuit on the left side compared to the series circuit on the right side? How can that be? Well, guess which one has more resistance to the flow of electricity?
The one on the left.
So think of these were cars. If you have cars and you have to force them into one lane, which is like the right side, all the cars have to move round and round in just one lane. Compared to if in a parallel circuit, it's true they have one lane here, but what happens when they reach this point? Some get to go leftward and the rest of the cars get to go rightward. Does adding another lane make more resistance to the flow of traffic or less resistance to the flow of traffic?
Less resistance.
Yes. Adding one more lane provides less resistance because they can flow more easily. They can go into their own lanes, right?
Yeah.
This is the reason why there's more current over here, 4 amps, because the resistance of a parallel circuit is less than the resistance of a series circuit because there's more paths over here.
Okay.
That allows them to speed up. Okay?
Mm-hmm.
So that's a big idea. Let's go back. Where's my pen? A parallel circuit will have less resistance. So the parallel circuit has less resistance, all right?
Yeah.
The way we actually can calculate it, I'm going to show you now, is this way. The formula that I'm going to show you is 1 over the equivalent resistors for a parallel circuit is equal to 1 over R1 plus 1 over R2 plus however many you have.
Okay.
All right?
Yeah.
So let me erase the idea and just show you how to use it because we're running out of time. We got 15 minutes. So in this case, if I go back to my app, we're focusing on the left side. We've got 2 10 ohm resistors, right?
Yeah.
In series, that provides a total resistance of 10 plus 10, which is 20 ohms, right?
Yeah.
In parallel, let's see what happens when we do the calculation. when we go back to here, if one of the resistors is 10 ohms and the other resistor is 10 ohms, then let's just see how that plays out for our calculation. 1 over the total equivalent resistance is equal to 1 over 10 plus 1 over 10. Well, what's 1/10 plus another 1/10?
1 over 20.
So 2/10. Yep, 1/10 plus another 10th is 2/10. All right, so you end up with 1 over the total equivalent resistance of your parallel circuit is equal to 2/10. And we want to solve for the total resistance of the parallel circuit. We don't want 1 over it. No one's interested in 1 over it. We want to know what it is, the total resistance, right? So the easiest way to go from here is just invert. Flip this side and flip the other side. When you flip 1 over R total, you get R total over 1, right? 10 over 2. And R total over 1 is just R total, right?
Yeah.
And 10 over 2 is 5, right? So the total resistance of the circuit is only 5 ohms. Because you've got two 10 ohm resistors. And the total resistance of that circuit is less than the resistance of even one of them. It's a weird idea.
Yeah.
Right?
Yeah.
So notice now, I'm claiming that using that new equation, you get a total resistance of 5 ohms. You can still use Ohm's law to figure out how much current should be flowing out of this battery right now on the left side. Well, the voltage is still 20. What is the total resistance? We said it was 5 based on that calculation, right? So 20 and 5. Let's go back to it and say, let's solve for the current in this parallel circuit. Should be the voltage of the battery divided by the resistance of the circuit. So the voltage of the battery was 20 divided by 5 based on, oops, what happened? Sorry, you said the 5 comes from our calculation we just did right here. Total resistance was 5 ohms. Tells us that the current should be 4 amps.
Yeah.
Right? And then when you go back over to our thing, you see how much current is flowing here. 4 amps. You see that?
Yep. See that.
And so the point is that amps is a measure of how much current is flowing. If you have a 10 ohm resistor right here and another 10 ohm resistor right here, then these two paths are equal resistance for the electricity to flow. And so that means 4 amps is coming in to this node. Remember, the node is this junction here where they all come together. 4 amps is flowing into it. Guess how much of that 4 amps is going to take the bottom path, and how much of that 4 amps is going to take the top path? Half, exactly. 2 amps is what flows downwards, and the other 2 flows upwards. And then when they recombine, what do they produce on the other side?
4 amps.
4 again. And the only reason it was a nice equal split of 2 amps taking the bottom path and 2 amps taking the top path is because both paths provide the same amount of resistance. And so they half goes one way, half goes the other. But remember that, have you ever heard the saying, electricity takes the path of least resistance?
Yeah.
So if I turn this top one into a 20 ohm resistor and keep the bottom one a 10 ohm resistor, along which path will we expect more current to flow once it reaches that node? You now have a 20 ohm on top and a 10 ohm on the bottom. Will you find more current on the bottom path or more current on the top path?
More current on the bottom path.
Yeah, you see that. 2 amps. Notice 2 amps is flowing on the bottom path, and now only 1 amp is flowing on the top path.
Yeah.
And that only adds up to what? 2 plus 1 adds up to 3. Why do you think it dropped from before it was a total of? Why are we getting less current? When I remember the change that I made was changing the top resistor from 10 ohms up to 20 ohms. So why did the current overall drop in this system? We started originally with just 2 10 ohm resistors and we had 4 amps flowing in this spot right here. But then when I turned the top resistor to 20 ohms instead of 10 ohms, the current right here dropped from 4 to 3 amps. Why do you think that happened?
Because If the resistor increased, wouldn't the resistance decrease?
Exactly. I took a 10 ohm resistor out and I put a 20 ohm resistor in. Is that adding resistance to the circuit?
Yes.
Yeah, and that's why the current dropped. So once you get that idea, also notice that more of the current went the bottom path because that one's easier to get through. It's the least resistance path. 2 amps went that way, which how much went the upwards? Only 1 amp. Right? And what do those add up to? The three that are coming in. When 3 amps come into a node, then they split up. And the sum of those, the current in those two paths will always add up to however much current's coming into that node.
Got it.
Right? And so the important thing that I want to leave you on, because I only got about 8 minutes left, is the best part of a the best part of a parallel circuit is that the voltage doesn't divide up. Remember, if we go back over on the left to our series circuit, the voltage on this battery was 20 volts. And then how much was it using to get through this first resistor? 10 of those 20 volts was being used to get through that bit. How much was being used to get through the next resistor? Another 10, remember that? So we had a 20 volt battery, but only 10 volts was being used on one resistor, 10 volts was being used on the other resistor. Notice what happens over here in the parallel case. 20 volts is how much voltage is on the battery. When we go test the voltage drop on this resistor, watch what we get. 20 volts. How much voltage is being used on the other resistor? Still 20 volts. So in a parallel circuit, all of the branches get the same voltage as the battery. That make sense? Might not make perfect sense, but it's just a rule that you would have to accept for right now. That the voltage on the bottom path is 20 volts, and the voltage on the top path is also 20 volts. It doesn't get split up like it does in series. There's new rules for parallel circuits.
Got it.
All right? So let me jot that into the note. In parallel circuits, gets the same voltage as the battery. So in the simplest case, this was a 9 volt battery. Splits into two, like this, comes back together like this. This side will be 9 volts, and this side will also be 9 volts. All right?
Yeah.
And so that's a rule that you have to know to solve the problems. Because the point is, could we now predict how much current is going to be flowing along this bottom path using Ohm's law? And the answer is yes. Do we know how much voltage is on the bottom path? It's got to be the same as the battery, 20 volts, right?
Yes.
Do we know how much resistance this bottom path has? Yes, 10 ohms. So remember, current is voltage divided by resistance, right? So what is 20 volts divided by 10 ohms? 20 divided by 10 is? 20 divided by 10.
20 divided by 10.
Because remember, the voltage of the bottom path is 20 volts, the same as the battery. That's what it's showing here with these two things testing this voltage drop is 20 volts. And the resistance of this resistor right here is 10. So what current is voltage divided by current. I didn't mean that, sorry. Current is voltage divided by resistance. So 20 divided by 10, what is 20 divided by 10?
2.
2. See how we calculate 2 amps? See that? And so if I went back to my over here to my drawing and changed this to show what I was just showing you, which I don't know why I picked the number 9. Let's pick the number 20. If this was 20 volts and this is 20 volts because it's a 20 volt battery and this is in parallel, and we knew that the resistance in both cases, if we go back to the picture, The resistance on the top and the resistance on the bottom were different, remember? This section on the top was 20 ohms, and then the section on the bottom was 10 ohms. So to find how much current flows along this bottom path, it'll be the voltage on the bottom path divided by the resistance of the bottom path. So the voltage is 20 because that's one of the rules. That's the rule that I'm just trying to tell you here, that in parallel circuits, voltage is the same as the battery on each of the paths. So it'll be 20 divided by the bottom resistance was 10 ohms. This was a 10 ohm resistance on the bottom path, and we get a prediction from Ohm's law that 2 amps will flow and take that bottom path. We'll go back to the simulation. You see that's how much we get, right?
Yes.
And then if we needed to predict how much current would go this way, could we use Ohm's law again? Yep, we can predict that 1 amp should go this top path. We just need to know what is the voltage of the top path. It's going to be 20 volts because that's the law, that voltage is the battery, and the battery is 20 volts, right?
Yes.
So we got 20 volts on the top. Well, what is the resistance of the top path? 20 ohms, right? And so the last part is to say, can we predict the current flowing through the top path? It would be the voltage on the top path divided by the resistance of the top path, and we get 20 volts divided by 20 ohms. Therefore, Ohm's law predicts that 1 amp will flow along that top path. And that's what we're getting, right?
Mm-hmm.
And those two amounts of current, 2 amp plus 3 amp, 2 amp plus 1 amp equals 3 amps. That's how much is coming out of the battery because it splits at that point. All right?
Yes.
All right, are there any questions? Because that is a parallel circuit in a nutshell. But we're just about out of time. We are out of time.
No, it's actually, I get it, yeah.
All right, all right. Just know that everything I've just reviewed with you is definitely in your textbook. The things that the way I teach it, not necessarily the way I teach it in the textbook, but all the main ideas and certainly the equations and then practice problems, those are all in every physics textbook. So you can reinforce anything I've done with you typically by reading through some of the chapter. I do recommend you doing that. All right? All right, Jeremiah?
Yeah.
All right. So I was just saying, make sure you check over your textbook to reinforce some of what we did.
Okay.
All right. All right. I'll catch up with you next week. Have a good night.
You too.
All right. Bye-bye.
Bye-bye.
All right. That concludes our 2-hour session on DC circuits, parallel and series circuits. And today's date is March 30th, 2017. All right, that's all for now. Signing off.